Good day, I'm Hansol Ko from the AI lab at Gachon University. I will now present the paper titled Grad-CAM-Based Feature Selection and Dementia Classification Algorithm Utilizing Voice Data. First, let's go over the context. The presentation will proceed in the order of introduction, datasets, method, GFM model, experiment, result, and conclusion. Let's start with the introduction. Dementia is a neurodegenerative disorder, and its main hallmark is a decline in cognitive function. This decline not only affects the memory, but also impacts on person's ability to conduct everyday tasks, making them increasingly reliant on caregivers. The statistics around this disease are alarming. As we delve deeper into this entry, the prevalence of dementia is escalating at an unprecedented rate. Current projections estimate that by the year 2050, the global population of individuals with dementia could soar to a staggering 135 million. The image on the left shows the population and distribution of dementia patients aged 65 and over in the US in 2023. This is not just an individual or family concern. It's a mammoth challenge that healthcare systems worldwide will need to confront. It's imperative for us to underscore the importance of early and precise diagnosis. Pinpointing dementia in its nascent stage paved the way for effective interventions, and timely treatment strategies can substantially elevate the quality of life for affected individuals. To address early diagnosis of dementia, an artificial intelligence-based dementia diagnosis has been proposed. Traditional dementia diagnosis relies on neuropsychological assessment or brain imaging techniques and cognitive evaluations. It was increasing interest in cost-effective approaches. To solve this problem, dementia classification through voice data analysis is proposed as one of the potential methods. This paper conducted dementia classification using voice data with three main objectives. First, enhancing the accuracy of dementia classification through feature engineering of voice data. Second, improving classification accuracy and building efficient model through feature selection. Third, visual confirmation of interpretative features in dementia classification. The method to achieve these three objectives are as follows. Feature engineering of voice data using MFCCs. Using transfer learning and Grad-CAM for feature selection. Model development enabling visual confirmation of dementia-specific feature including both. This research is expected to contribute to the development of more accurate and efficient models for voice data analysis. This is datasets what we used. We employed a dataset obtained from AI Hub, which consists of audio recording in WAV format with a sampling rate of 48,000 Hz. The dataset includes 11 scripts and their corresponding responses. In table, question 1 to 3 are read-along sentences. Question 4 and 5 are picture description tasks. Questions 6 to 8 are word memory tasks, and questions 9 to 11 are free expression tasks. The data was collected from a total of 292 participants, including 121 from the normal group, 89 from the Alzheimer's disease group, and 82 from the mild cognitive impairment group. The duration of the voice data range from a minimum of 3 seconds to about 1 minute. For question 1 to 4, the duration is within 30 seconds, and for question 5 to 11, it is up to 1 minute. We used MEL spectrogram as a way to pre-process this data. The prepared dataset is processed using MEL spectrogram function to convert the audio file into image file. A MEL spectrogram is a representation of a sound signal where the frequency scale is MEL scaled. For each audio data, we compute the MEL spectrogram, the average MEL spectrogram of the harmonic and percussive components, and the delta of the MEL spectrogram. The 3 transformed image files are used as inputs. For the purpose of comparing accuracy based on inputs, both the combined image and individual images are utilized. Next method is transfer learning. To leverage pre-trained representation or feature extracted from a deep neural network trained on a large-scale dataset, employ transfer learning. Transfer learning allows us to capture general pattern and visual representation. The model is fine-tuned using the BridgeG16 architecture. Next method is Grad-CAM. Grad-CAM is an attention-based visualization technique that enables understanding of the region in the input data that contributes significantly to the classification decision. Unlike CAM, Grad-CAM generalizes to CNNs without requiring the global average pooling layer, and instead utilizes fully connected layers. We differentiate areas of high importance using Grad-CAM and visually interpret the feature inherent in the voice data. Next method is feature selection. We select the area of importance identified through Grad-CAM. Only the features from this selected area are used for feature selection during the training process. The important feature areas are replaced with 1, while other areas are replaced with 0, and then multiplied with the final layer's feature map. The model that incorporates all the methods is referred to as GFM. Audio files undergo pre-processing using MFCC, converting them into 3 types of spectrogram images. These 3 spectrogram images are then fed into the BridgeG16 model for feature extraction. During this process, important feature regions are identified using Grad-CAM. From this, an area map is created that retains only the selected crucial regions, which is then multiplied with the feature maps of BridgeG16's COM5 block. The resultant feature maps, containing only the essential regions, regions are passed through a flattened layer to enter the dense layer for training. This constitutes the GFM model. The experiments were conducted in two main categories: classification based on input and classification based on the model used. Under the classification based on input, there are four types: male spectrogram, average of harmonic and percussive values, delta value spectrogram of the male spectrogram, and image combining the three spectrograms. For classification based on the model used, there are two types, using only VGG16 fine-tuned and using GFM model. This is the result. First, comparison of classification accuracy based on input prior to feature selection. The results demonstrate higher accuracy in all classifications when using the combined three spectrograms compared to individual spectrogram. It confirmed the effectiveness of feature engineering using MFCCs. Next, comparison of classification accuracy based on input after feature selection. The results show an increase in accuracy in all classifications. It confirms the effectiveness of feature selection using Grad-CAM. So, here is our conclusion. Through the result of the experiment, we find the combined image of three types of male spectrograms exhibit an accuracy increase ranging from 1.3% to 9.4% compared to individual images. And the feature selection through Grad-CAM also led to a classification accuracy improvement of 2.9% to 6.1%. The GFM model, which combines both approaches, achieves an average classification accuracy increase of 9.5% to 12.2% compared to individual spectrograms before feature selection. Therefore, the conclusions that can be reached from the above are as follows. Various aspects of voice data features have a significant impact on dementia classification. Attention-based mechanisms are effective in classifying dementia. Temporal features of voice data are high importance in dementia classification. In summation, this research underscores the paramount importance of vocal characteristics in dementia classification and the transformative potential of feature selection using Grad-CAM. As the medical community continues its endeavors into the early detection and treatment of dementia, leveraging such advanced methodologies and insight will be indispensable. And this is the references for the presentation. Then if you have any questions, please send the email to us on the address provided below. Thank you so much for listening.